Okay. Hi, everyone. So welcome to another week of these webinars. So today we have Fabian presenting EGNNs for like molecular simulations. So if you have any questions, please just write it in the chat. I didn't ask you. Do you want me to read them throughout or wait until?
Yeah, just go ahead. I mean, I think it's always good to kind of like ask questions as we go, because otherwise, if I lose you, then we can stop basically, right? So yeah, please ask questions.
Okay, sounds good. Then yeah, you heard it. So if you have any questions, just use the chat or raise your hand, I guess. And yeah, I think all yours.
Yeah. Okay. Thanks. Thanks, Louis, for inviting me, and also thanks for organizing the webinar. As I said, it's quite nice to have a place where we can come and have exchange ideas, and even for different time zones and different backgrounds as well, probably. Yeah. So thanks again for having me. And today I'm going to talk about some work we've been doing at IBM Research together with our partners at STFC in the UK for, I would say, roughly 2 years. And it's about, as you said, it's about molecular dynamics, accelerating them. But we're doing a bit of a slightly twist to like modern machine learning potentials and trying to basically bypass force calculations using equivariant autoregressive networks. And I thought, a second, yeah. And I'm, given we all come from different areas, I thought maybe good to motivate a bit. Why would we want to simulate systems, or why would we want to accelerate simulations in the first place? And I, recently I came across this kind of work by the Paisani group in Nature Physics, where they are interested in kind of detecting the phase transition in supercooled water. And they run simulations for this, 256 water molecules in a box. They throw it in, they run it for a bit, and what they are trying to observe is, well, how does the density change over time at different pressures? Let me get my mark out. Yes, sorry, that was the wrong. Yes, and we can see this basically here. And while maybe a lot of people would look at the kind of like the density profiles, for me the most striking thing in this plot is the x-axis, because it shows you the time in microsecond. And if you have a background in atomistic simulations, you'll be like, well, microseconds are very hard to achieve at a high accuracy. So you go to the paper and you look at the abstract, and you see, well, okay, microsecond simulations, chemical accuracy, and then you see, shit, took them like several years on supercomputers. And, very impressive that they had the patience to do this, and very impressive findings. But obviously that basically really bears the question, can we afford to do science in this kind of pace? And is there a way we can speed up these things? And this is basically what the talk is about today. So we're trying to start with the questions, what took them so long, or what would take any of us so long? It's not like this group in particular. I want to stress that it's like everybody who's trying to do microsecond long simulations with classical MD would struggle to do that. So just as a bit of background, what is actually the input for an MD simulation? You would have like your system. In this case, we're following the Paisani group and saying we want to simulate some water. We have a certain number of atoms, N. We have the atom types, in this case only oxygen and hydrogen. We have positions, and we have the velocities. They are both vectors. And what we're interested in is, how does the system evolve over time in 1 microsecond? The Paisani group simulated 3 microseconds. Let's focus on 1 for now. That's challenging enough. And the question is, how do we get from here to here? And the nice thing about MD simulations is we know how to get there, because we can just we have the tools to do this. We have Newton's equations of motions, which describe how atoms evolve, in space, in certain environments. And probably most of you have seen this equation before. We basically just have a second order differential equation. The mass times the acceleration is equals to the force. And the force can be expressed as the negative gradient of the potential energy U. And you can already see that there might be already like one problem, because it is a many-body function. It depends on a lot of different positions of basically all particles N, ideally. How do we usually kind of go about like solving this equation? Well, we numerically integrate it in MD simulations. One of the most common algorithms for this is the velocity Rayleigh algorithm, implemented in like most common packages like LAMMPS, ASE, and so on. And what we basically do is we say, given the current state, t, we predict new positions and new velocities at a new state, t plus delta t. And you can see already, well, okay, there's some stuff in velocities, go into the positions as well, but there's also some kind of terms I color-coded in different colors. And this is where the catch comes in MD. The first thing is you have this kind of higher order terms you neglect, because you usually truncate here, which means the larger you use for delta t, meaning the faster you want to run with fewer steps from here to here, the larger your discretization error becomes, because that scales with cubically with the time step. What does that mean? Well, we have to do a lot of very, very small steps. So we basically evolve this frame by frame, and the interval between them, usually for water or anything we have hydrogen, is 0.5 femtoseconds. That means to go from 0 microseconds to 1 microsecond, you will need like 2 billion integration steps. And maybe we don't have a feeling for this. If we think about operations, we do when we, I don't know, train like a multilayer perceptron, maybe there's also quite a lot of operations. We do a lot of forward passes. It won't be that bad probably, right? Well, let's see. The other thing is that we need the forces here. And we already mentioned before that the potential energy depends on a lot of different atoms. So we need to take into account the environment of each atom to basically get the forces. If we use like machine learning potentials, we would do that by a backprop, something to keep in mind. Otherwise, we can just say like the gradient directly with an analytical function. So the problem is, based on this, if you want to have accurate forces, this will be quite difficult to get at a low cost. So usually we would like to have like quantum mechanical accuracy, and there's like the more accurate you want it, usually the more you pay for it. There's this kind of famous scaling. I think Anatole von Linienfeld had like a similar figure once. That's I think where we had this from. Basically, you show the accuracy on the y-axis, in this case an energy error, and on the x-axis you show how expensive it is to run like one compound. And you see here you have this kind of like nice scaling curve, which kind of starts at Hartree fork, then you have MP2, and then you have like the gold standard quantum Monte Carlo or coupled cluster accuracy. You can see, well, things are getting quite expensive then. Then you have DFT, density functional theory, which kind of like breaks this scaling, which is one of the reasons they got the Nobel Prize for this. And you basically get better accuracy for less kind of compute. And then we have now, I would say since around like 2007, like early days, but then in the 2010s and like now definitely, we have the machine learning potentials, machine learning atomic potentials, MLIPs, which really kind of completely are off this kind of diagonal line and allow us to kind of simulate quite fast. We are now even in the position we can train foundation models, which cover the entire periodic table. One of the most famous ones, or current, like state-of-the-art ones, is the Maze family. They've trained this on the MPTRJ database from the Materials project, and we're able to get qualitatively stable simulations at these kind of different systems. We might be able to fine-tune them to get like quantitative accuracy, but things are actually quite good, and like we're way off this like diagonal. So, well, why don't we just like use one of these models and run our simulations in MD for our water? We do our microseconds. Surely that can't be too expensive to work with these models, because they're much better than all of these, right? Well, so the force is accurate with this one, so we're happy with this. The problem with this is that the Paisani group is already using one of these machine learning models. Not Maze, they have their own in-house version, MBPol. But even with like state-of-the-art models, we are now about like 1 nanosecond a day for 1,000 atoms, assuming like 256 water molecules. That's around 800 atoms. It will still take some time, like probably years, to get like a microsecond, let alone like 3 microseconds. So we need to kind of do something differently, and that's why we at IBM have decided to kind of tackle the kind of time step rather than the force. And the idea is basically, well, let's ignore the force for now and just like try to predict the new state directly, rather than like trying to predict the force and plug it into like a velocity VLA algorithm and then run with that. So what we're doing is basically we say the new position, the new velocity is not what we see here. This is in gray, we show the velocity VLA, but we approximate it with 2 functions which depend on the current state, so the current atom types, positions, and velocities for both cases. The kind of time step you want to go with, so how much you want to predict into the future, and some parameters detail. So that's basically the idea. And you can see that these terms, first of all, do not depend on the forces. So we don't have to do any backprop if we predicted the potential energy. But also, and that's the kind of idea behind all of this, is that we could in principle be able to use way larger time steps than the integration time step, because we can just like train on multiple integration steps from the MD and then just like predict basically M times delta T. To visualize this, here's a trajectory of a benzene molecule over 1 nanosecond, and now you can just imagine that instead of having to walk through each of these states, color coded here in green, we're able to jump between the kind of red colored frames, and that could hopefully speed up things by just having to do that every kind of like, skipping like, I don't know, 10, 20 femtoseconds or so. So that raises the question, obviously, cool, this is a nice hypothetical thought. How would like an architecture look like, and how would you kind of like confine or constrain these functions? Are there any kind of physical problems or constraints we have to kind of account for? And how would that actually perform? So it took us quite a while to kind of come up with some, some architecture, but we were pretty sure what the constraints are at the beginning. And we are focusing mainly on two aspects, which is physical consistency and generalizability. The first thing we said is we want to model NVE simulate, or the NVE ensemble. So when you simulate, you can usually keep different, let's say, properties or properties a constant. In this case, we're saying we simulate in the microcanonical ensemble, which means we have a constant number of particles n, constant volume, and constant energy. So far, this doesn't change anything from what I've showed you before, because Newton's equations of motions intrinsically produce this ensemble. So that's nice. The reason we're doing this is, first of all, because it's deterministic, so we can directly predict the next step. There's no kind of noise added as if you do like in a thermostat, if you wanted to simulate at a constant temperature. The other thing is, in the NVE ensemble, you have certain conservation laws you can incorporate directly, and you can basically constrain the output of your model to, for example, that the total linear and angular momentum are conserved. Another very important property also for performance is incorporating certain symmetries into the model. I'm sure you guys, I mentioned maze now, but EGNNs are around for a long time now, so I won't spend too much time on this. Basically, the idea we want to achieve is that the model architecture is equivariant to rotations in three-dimensional space. So if you take a benzene molecule at a time t, and you have your function which predicts where are the kind of positions of that molecule at time t2, and you now rotate that thing, you basically want to make sure that this condition holds. Basically, that if you rotate the input, should be equals to the output, like rotated. You just basically want to make sure that you don't have to do like data augmentation or anything, but you also can use higher order features which could help like the expressiveness of the model. The last thing we were also quite one of the kind of key concepts when in the original papers in machine learning potentials is transferability and scalability. The problem is we can only do very high accurate calculations on very small systems, as I showed before. So the problem is we need to kind of have an architecture which can scale, meaning you can learn from small examples and then do inference at large kind of samples. If you want to, for example, you want to train on small molecules, but maybe you want to predict a protein where you could never do ab initio calculations. So we're basically kind of driven by this constraint. We want to make sure that you have scalability and transferability in terms of size, but also in terms of like, chemical space. That, let's say, if you train the model on benzene, where you have, the local environments of this carbon atom is very similar to naphthalene. So you should be able to, interpolate between these and be able to kind of predict something here, at least qualitatively, if you train these together. It should not be like completely new. You don't want to be constrained. You don't want to constrain your model on the number of atoms or so on. Right. So based on these constraints, we were starting, to develop, talking to people who do actually simulations, talking to, to the people who are on the ML side. And we basically decided, well, the first thing to do here is really is more like a proof of concept. We try to kind of come up with like an autoregressive workflow. How can we really speed up the simulations? Is it actually going to be stable and so on? So the architecture we come up with is as follows. We have at time 0, we have a certain kind of state. In this case, let's say we want to model this molecule. This is paracetamol. So I'm sure you guys know this one. And we start with having some kind of atom types. We have the velocities and we have the positions. This is the same as we have for any MD simulations. And what we want is we want to predict how does this state look like at a later time interval delta t, which is defined by r delta t and v delta t. So far, so good. And we're basically saying, well, we're gonna express this thing here, this kind of gray box, to kind of like conserve all the constraints we discussed before. This, like, the best we can do here is like an equivariant message passing neural network to kind of learn these functions to produce these kind of like new positions and new velocities, where we're basically having k-sequential message passing layers. We're going to come to this, what that actually means and how like the message passing looks like in here. But this is basically the idea, and this is like basically the same as Nequid maze. It's just like the kind of core architecture. And the idea is that basically you learn the environment of all these atoms, but here we not only learn the kind of like topology where atoms are, but we also take into account the velocities they have at every moment in time. And the idea is to learn these and then basically correlate that well in the end, that they can be used as a regression for the target properties. All right. So the first thing we need to do is we need to come up with an embedding based on our attributes we're having. So this might look very familiar for you if you're like familiar with any of the MLibs. So we basically have like a node and an edge embedding. You usually incorporate the edge as a kind of a radial part shown here in radial basis functions and spherical harmonics for the angular part. And the node in most machine learning potentials is very simple, just like takes the atomic kind of numbers or the chemical elements and does like one hot or something. Here we can also leverage the velocities because we can basically take the radial basis embeddings, but we can also incorporate like higher order features in the initial kind of node embeddings. And with this, we basically can enter the message already, having already information about the velocities of each node separately. Then this is very similar to message passing in the Nequid architecture. We're basically just like learning the topology, what atoms are around us and what attributes do they have. But in this case, we also have the knowledge of the velocities from the previous stage. And then we go to the update. We basically take these messages. We are pooling them all together. And here comes in something we borrowed from the SEGNN architecture from Johannes Brandstätter, where you can basically say to kind of incorporate additional information on the node level, particularly if it's vectorial properties like a velocity. You can condition these using a second tensor product based on the spherical harmonics embedding weighted by the radial basis. For this, we have another nonlinearity, based on a nonlinear gate. And with this, we basically get our new features. And we are then basically, once we did that, k times, we come out, we take our kind of final embeddings of the local environments, pass it to a readout function. What I should say here, you can see here a delta R. So we're not directly predicting the new positions, as I said before, just because we want to ensure translation variance. So it's always better to predict relative distances. That's the same thing we do with like, when we define edges and so on. So the only thing we do is we say like, we don't have G R, we have G delta R, and that's basically just like a relative displacement we're having. And basically, once we have our initial guesses, we can then incorporate final constraints, making sure we follow total conservation of momentum and linear and angular momentum. So yeah, that's basically the idea, and we can incorporate directly. So because these are hard constraints, the model will always obey these constraints. So, well, how do we train this model? First of all, I mean, yes, you need data and so on, but the idea is basically very simple. You just start, you run like in the level of reference you want, you run MD simulations, you generate a trajectory, and instead of having a label of an energy, forces, and maybe stresses for materials, you say, given my current positions and the atom types and the velocities, what is the new positions or the displacement and the velocities? That's all it. That's your data set, and that's what you're trying to minimize the loss for, basically. So basically, the model only predicts one step at a time, given a certain input. The problem is you're going to call this model during inference a lot of the times, right? Let's say you want to run 1 microsecond. And let's say delta t is, even if it's like 100 times larger, you still have to do hundreds of thousands of inference passes. And we know already, like those of you who have worked with like autoregressive models, is that the more often you kind of call these things, there's error propagation, errors accumulate over multiple steps. We even know this from like classical MD simulations, that if you run MD simulations, you will never kind of get the true trajectory due to the discretization error. In ML models, this thing are even worse, because we might even like get out of the kind of domain the model has seen during training. We might have to do extrapolation, and then we basically completely lose it, and we have this kind of catastrophic instabilities. So if you want to have an analogy, you can think about this kind of like telephone game. You start somewhere off, which is nice, but then if you kind of play this over rounds and rounds and rounds, at some point your model will break probably. So the question is, will this really work, this kind of architecture in this kind of way? I will show later it does work in NVE, but we also try to address this problem. And we do this actually by doing a trick we've seen from people at DeepMind, where they built a surrogate model for CFD, and they show that injecting noise after every step actually helps to stabilize the system and make sure that you're basically staying in a data regime you've observed during training, or like at least kind of like similar phase space. And the nice thing about molecular simulations is that actually noise can be your friend, and it's actually not just noise, but can allow you to lift or to kind of change the ensemble. So as I mentioned before, we reject the model on learning NVE kind of data, but we can use a thermostat after each step to kind of lift the kind of system, the states to the NVT ensemble by introducing noise. So what we do is we have a CSVR thermostat, which is one of the most commonly used thermostats, which basically rescales the velocities our model predicts, which are NVE velocities. They obey the conservation of linear momentum and angular momentum, and we can rescale them every step based on a certain canonical distribution, which will follow a certain temperature. We can basically set as a user, and we should basically set to something we've observed during training, plus minus maybe 30, 50 Kelvin. And then we can basically just like update this, and we can continue doing this. And then we basically lift our model, which has only seen NVE, we can produce NVT. That's the idea. I will show that this works, but this is not only allowing us to go to NVT, which is usually where you want to run MD simulations, because you want to basically mimic experimental conditions, and most experiments are done at controlled temperature rather than in controlled energy, because that's very hard to measure. And if you do this correctly, you will also reproduce the Boltzmann distribution, which we'll also show you later. Right. So just to summarize, the idea is that the model has been trained and produces NVE data, but in inference, you can couple it with a thermostat to get NVT predictions out of it. So how do we validate this? And there are two different ways. As I said, I will show you NVE and I will show you NVT. So we will start with NVE because it's just easier to kind of show how good or how bad the model is. Because in the NVE ensemble, we can just like start, say, here's a starting point. We run a simulation with our reference method we trained our model on. And then we compare the configurations we get out with what our model would produce. And ideally, they would be perfectly aligned. To do this, we take our example of paracetamol. And instead of tracking each position separately and getting like 20 three-dimensional plots, we're tracking certain metrics here. We get the and we're tracking basically a distance between the two oxygens here. We're tracking the distance between the nitrogen and the hydrogen here, and we're tracking an angle. We chose these different kind of geometric metrics just to get like different frequencies resolved as well and see, is the model actually able to resolve everything with the same level of fidelity? And basically, this is what we find. So each of these plots corresponds to each of these metrics. On the x-axis, we show time. So we run for 500 femtoseconds. That's 1,000 MD velocity Vallée integration steps. And we're showing in black. I hope you can see it. If you can't, that's a good sign, I'd say. We're showing in black the MD reference at the time step of 0.5 femtoseconds. We're showing in blue the crash prediction at a time step of 0.5 femtosecond as well. And then we're showing the largest time step we investigated here, which is a time step of 7. So that's 14 times larger. And we're basically plotting it all over each other. And at least for these shorter times, you can see that the model actually really captures the complete dynamic behavior of the system across different frequencies, which we were quite impressed by. Obviously, I haven't shown you anything beyond like, for like 100,000 steps, things might look different and you might start losing things due to error propagation. But this is really to validate that the model has really learned and understood how to kind of evolve the system according to Newton's equations of motions. How do we validate the model for NVT? That's a bit more tricky because, as I said, we will introduce noise. So you can't really compare configurations against each other because these will inevitably diverge. So the configurations will never be the same. Rather, we need to kind of compare ensemble averages or distributions of properties and check how do these models kind of reproduce these. And that's the same thing we would like, benchmark an MLIP nowadays. We would always go beyond MAEs. Maybe do like geometry optimizations, but if you're interested in really like understanding what the model does, you would run a simulation and you would compare an RDF, which is always an ensemble average as well. Okay, so in NVT, we're going to go a bit more into detail because this is what you really want the model to perform well in, because this is what you're going to use it for mainly. And to do this, we kind of look at 3 different systems. The paracetamol, I've already kind of like, introduced you to. we're going to show you quartz, just to have like, a solid reference, and also water to have a liquid, just to see like how does the model perform across different phases, across different chemical spaces, and across different frequencies and dynamics. Here are some details on how many samples we used for each of these models, how many atoms there were, what are the reference in these steps, and most importantly, what is the forecast time step? So how much can we speed it up? So basically, the largest time step the largest enhancement we achieved here was for quartz by going from like 1 femtosecond to 30 femtosecond. So it's a 30x speed up in the time step. Right. So I will start with paracetamol. There's multiple things you can test for each of these kind of systems. We're trying to be kind of as thorough as we can while making sure we don't have to spend a lot of compute on it. So we will validate based on simulations, and we're looking into properties which are involving dynamics, energetics, and kinetics here for the molecule. The first and most important thing really is that when you run this, so we basically run simulations in MD to kind of get some kind of reference data for MVT, but we also use the model with the thermostat and run it autoregressively. And we run paracetamol with a time step of 7 femtoseconds for more than 1.1 million steps. So that's a lot when you think of autoregressive models, and it remains stable throughout the entire simulation, which is a good starting point. So we thought, well, then we look at the properties. We look at the VDOS, which is the vibrational density of state. This is just like if you take the autocorrelation function and you take the Fourier transform of it, which just like tells you how are frequency distributed for different elements. So we resolve that per chemical element. That's why for paracetamol, we have it for hydrogen, for carbon, nitrogen, and oxygen. And we see the MD reference. We see that in the dashed line here. And we see Trashcast reproduces that very well across all elements, which is nice. There's also a way you can compute like an overlap score. We did some work on this like a while ago, and the overlap score of like how similar are these or like are these spectra is at around like 95-ish%. So we're quite happy with this. Then, even though our model doesn't really have an energy kind of metric or like doesn't predict the energy, what you can do is you can take the samples produced by Trashcast with the thermostat and take these and pass them back to, in our case, the force field we've been using to kind of generate the data and see, does the distribution of these energies, do they follow the distribution of the MD reference NVT simulation? And we find it does. So that means basically that our model is able to reproduce the Boltzmann distribution, which is mimicked by the NVT simulations. So we were very happy with this as well. But then we also thought, well, we need to go hard. We need to like do something like more difficult because these things are all like, maybe like too easy to get. So we thought, well, what can we do? We can look at something more subtle, something which is also hard to get maybe for machine learning potentials. So what we do is basically we sample the free energy surface, and we're interested in kind of, this maybe from like a lot of peptides or proteins that you kind of do these Ramachandran plots where you plot like two different dihedrals and you check what kind of states does the molecule like to be in. And this is like a free energy surface. So we are kind of tracking two dihedrals. We're tracking the dihedral here at the hydroxyl group, just formed by this kind of little purple box here. And then we have the kind of amine group, which we're showing here. And we plot basically this on the y-axis. We plot the hydroxyl angle on the x-axis. And then we just like count how often do we observe these configurations in our trajectories. And then we can just like, take the logarithm of this. And this is basically related to the free energy. And what you can see is that we're able to resolve that very nicely between Trashcast and MD. Qualitatively, there is no, for me at least, it's very difficult to see a difference. And we thought, well, this is one thing. Can we also see if we can like reproduce energy barriers quantitatively? So we're doing kind of some cuts along here by fixing one of the angles and just like seeing basically what is the probability of finding these states. And that's what we're showing here. We can see that both of these cuts or both of these kind of barriers are very nicely resolved across. And I think even this quantitative agreement, that was quite impressive for us and really shows that the model has really learned beyond what it has seen in the training. Because I should say, it's not shown here, but we have not observed this kind of flip of the amine group particularly, which is like quite a high energy barrier here. So basically this, I don't know if you can see this, but of this kind of nitrogen going from pointing with the hydrogen pointing downwards to pointing upwards. So this thing, the oxygen would point down. That we don't observe this flip So basically, we don't observe these configurations in our training set. We only have these. And I think that's quite impressive that the model is able to kind of extrapolate there and kind of predict that flip, not only observing it, but also getting the kind of like right frequency of occurrences here and getting the right values. Right. Enough about paracetamol, because I mean, you don't want like, we can simulate molecules quite long now and quite efficiently. What about something more in a bulk liquid or bulk crystal? So for quartz, as I said, we get the largest enhancement and the largest kind of speed up. We can use a 30 femtoseconds time step. And, you know, we run this thing here, which is like, you know, way larger than the paracetamol. It's like 162 atoms. We run this for more than 550,000 steps, still stable. We compute the VDOS as we did before. And we observe the kind of same trends we observed for the energy distribution. So I'm rushing through here because there's nothing really, you know, unexpected. The model really performs well, even if you have like a periodic crystal, which is very nice. And we have like such a large kind of time step. And we only use like 5,000 training configurations of, you know, this system. So I think you can even like stretch that further with like future architectural developments or, you know, having more training data. Or we will come to this. Very importantly to say is that we basically only, you know, validated the system for the original size, but we could also run supercell sizes. As I mentioned before, there was one important desiderator for the architectural design. We can run easily larger systems than this, and we have some scaling laws for this in DSI. If you guys are interested, we can, you know, just we're not fixed to the number of atoms. Right. As a last example, I will show you some liquid water. So this is as close as we will get to the Paisani kind of like systems they studied, although this is at room temperature. And we chose the system as well because, first of all, water, you know, because it's a liquid, there's more, you could say, random motion in there, but you also, it's the only system we really have where we go beyond intramolecular interactions, but go to interactions between molecules and between systems. We run this again for 550,000 steps. And, you know, we're able to produce the VDOS quite nicely. This is nothing new. I showed you that before, so probably not surprised to see this. But we also basically went into the kind of system and really computed then some dynamical properties like the diffusion coefficient based on the mean square displacement. And we can get very, very close based on the predictions here. And yeah, for us, that was quite nice to see because, you know, MSD and the diffusion coefficients is something usually quite hard to converge, and that the model kind of gets that as a long time behavior as well, because, you know, we kind of correlate the mean square displacement over 10 picoseconds. So this is for the model with a 5 femtoseconds time step. It's like 2,000 steps, and that gets quantitatively quite correct. Is good to see for us that the long-term behavior is well resolved, as well as the kind of short-term ballistic regime as well. And then finally, we also looked at the kind of structure. How does water structure in average over like in 300 Kelvin at room temperature? And you can see that we resolved that quite nicely as well across all kind of element pairs. So yeah, and that's all I have to show you in terms of like, you know, molecular systems. But the story doesn't end here, because we were very happy to see the results, but we were also trying to understand, so why, you know, you can see I use different time steps for different systems. We have different number of data points or different number of like different sizes of training samples. So we're trying to understand, what does the model actually learn? What is easy to learn? What is difficult to learn? So we are basically trying to see how much can we really push that delta T based on the number of data points we're using. And yes, so what we're doing is basically the following. What I'm showing you here is how does the error for each of the system behave as a function of the time step multiple. That means how much larger than the original MD time step. And we can see that here we resolved for like 1, that's the MD time step, twice the MD time step, 10, 20, and 30. And as expected, I guess, you would expect that like the more you try to predict in the future, it always gets harder. It's like with the weather, right? You can't, if you ask you how is the weather next year, you're gonna struggle. But if I ask you how is the weather in like 10 seconds, it's probably gonna be very easy. And that's the same thing we're seeing here. What is interesting is that we see quite some variations across systems. But before I go into this, I wanted to give you a quick kind of like intuition. What do these kind of relative velocity MAEs correspond to? Because, you know, we're always used to kind of seeing these parity plots, but then what does it actually mean? How does it correspond to kind of behavior stability and so on? And what we find is actually, I'm showing you here for water, the parity plot for 0.5 femtosecond, which is like the normal time step, and 15 femtosecond. And I think most people who have ever trained machine learning models would say, well, okay, the 0.5 femtosecond is pretty good, but even the one with 15 femtosecond, that's I would take that correlation plot for my model. The point is, when we run simulations of this, it's not stable. So what we really find is that even seemingly small errors can cause instabilities in the dynamics, because you run it that many times, and even then the thermostat is not able to push it back. So the naive strategy to overcome this and say, like, you wanted to run your water as Paisani did, but now with like 15 femtoseconds, can you achieve this by adding more data? So the next question we can ask is, how does the accuracy depend on the number of data points, which is quite common to do these kind of scaling studies when you do this. I think the early machine learning potentials, at least when they went to develop the equivariant ones, they also did these kind of things. So what we're doing is basically for each of the time step multiples we're kind of seeing here, we are looking at how does the model performance improve by adding more data. We do this by kind of plotting for each of these time steps. We're plotting for different number of data points, these curves, and we're extracting the slope. The TLDR is the more negative the slope, the faster the model will learn. Okay, a slope of -1 means if you increase the training data set size by 1 order of magnitude, you will get 1 order of magnitude better MAE. That's the idea. And you can see that, first of all, there is a clear trend or clear distinction between different systems. And that is, when you maybe first see, like, wow, that's very surprising. But I think we explained it in that way that probably with quartz, I mean, the quartz is a solid, right? The vibrations you observe are not necessarily, you won't see that many new environments, first of all, from the structural side. But then also you have the kind of certain frequencies. So model displacements will always vary between points. So probably it's going to be very hard for the model to estimate how many kind of intervals has each individual atom in the solid traveled, even though the configurations look very similar. So that's why this thing saturates very quickly. For water, you can see we kind of get a bit of like an improvement here at the beginning, but then we also saturate quite quickly, which makes sense because water is way more random, and like the more you predict into the future, like atoms might come into like the environment, get out again, and so on. So it's very hard to predict. And paracetamol, obviously, at the beginning there's no interaction around it, so it's only confined by the intramolecular interaction. So that's why it might be easier. But over time, it's still difficult because sometimes the surrounding atoms can also help you to learn because they serve as a kind of a boundary rather than the model, the atom could explore the entire space around it. What is interesting to mention, though, here, apart from like system comparisons, is that compared to machine learning force fields like NeckWeb, they did this comparison, we get 4 times larger slopes than them. And our intuition behind this is that by using the velocities as well, obviously we have way more information. So that means that by adding more data, we can also extract more varieties in the velocity spectrum, which could explain why the model learns more by adding more data. That's at least our interpretation to it. Right. With this, I will leave it here probably, but just to give you like a quick kind of like conclusions and like some take-home messages. So we developed this kind of new generative framework we call Trajectories to accelerate, how we can simulate systems and get like, MD trajectories faster in shorter time, hopefully. I've shown you and hopefully convinced you that we can do this for a variety of systems, at least 10 times with 10 times larger time steps while maintaining the accuracy on the property level, very importantly. However, there's still, much work to be done, like, using multiple time steps, incorporating more physics. I know that other kind of groups work on this right now. So yes, this is great. The community need to push on this together. And I mean, this is not there. This kind of field of bypassing the force and the integration is in its infancy. So it will take time to pick up properly, but we need to start working on this now. And just to give you like kind of like an insight, how much faster is this? Or I told you before that we can probably right now produce 1 nanosecond a day for 1,000 atoms. So we try to kind of do some similar benchmarks, and we did it for quartz and water, which we scale to the supercell sizes. And you can see that for quartz, for example, with like, a bit more than 1,000 atoms, with this kind of method, we could get like 35 nanoseconds. If you go even like above 4,000, you get like 18. Water is a bit more difficult because also we use larger cutoff. But even then, we are like, still faster. And I think, we could like still improve on here. And when you look at the machine learning potential community, this community is really like, you know, pushing the limit right now, and it just takes time to kind of develop these things. So I think this is just the beginning, and hopefully we can push this even further. And then hopefully this will, in the long term, really cut the time to obtain microsecond trajectories from years, weeks, months, and maybe we can push even on this. So yeah, with this, thanks again to Luis for inviting me, and also obviously to all the co-authors, Thiago, who I know is here. A lot of the work on, like, you know, making these nice figures. So if you like the figures, that's Thiago's work. Max, who did a lot of stuff on the architecture and the maths behind it. Zin and Juan, who generated data and helped with kind of like the constraints in MD. And Fausto, who, you know, helped with everything on the kind of like physical constraints on the model as well, and making sure like the validations are properly done. And then a lot of people we had discussions with. And yeah, feel free to check out the code. It's all open source. There's an example notebook. Yeah, and I'm happy to take any questions.
Awesome. Thank you so much. That was a pretty clear presentation. I really liked it.
Thank you.
If you have any questions, just write in the chat or raise your hand so you can unmute yourself. I have a few on my sides. First, with respect to the training data.
Yes.
I believe you can, there are two different axes. One is like the time steps. Like, for example, you can train with like, you can just extend the time steps and augment the data like that. And another axis is like to bring in more configurations, like different small molecules or etc. So when you say they're scaling training samples, which axis are you talking about?
So sorry, maybe I should have made this clearer. So this one here is always taking the same number of training samples, but we use different time steps. So that's why it's easier to learn different time steps. That's just to show like under the same conditions. And this one shows, maybe I can show you this one. Let me show you, this is probably clearer. This is basically for displacements and velocities. And what you can see here on the x-axis is the number of data points. And then based on the coloring, you can see the multiple of the MD time step. So as you go on the x-axis to the right, you increase the number of or you increase the data set size you train on. And if you go up, you increase how much you go into the future.
But by increasing the number of data points, you mean bringing in new configurations, new
configurations at that time interval.
At only that time interval.
Yes, so that's a good question. So basically, yes. So I think in GraphCast from DeepMind for weather forecasting, they basically try to learn a larger time step by a sum of small time steps. Is that what you're trying to ask? Yes. So if that's that, yes, that's something for the future. So right now we're not doing this. We only learn on one time step only.
Okay, yeah. So for each of these lines, then it's a different Trashcast model.
Exactly.
Okay.
Yes, but like in principle, it's just we wanted to kind of get a clean architecture and a clean kind of benchmark first. But in principle, you could use an positional encoding of the time step, and then basically train on all of them at once, and also incorporate constraints saying you have 1, 2, 5, and then you try to construct saying like this 5 femtoseconds time step is 5 times that 1 femtoseconds time step. And with that, you could also get like consistency of the model probably. So that you could do as well.
Yeah, exactly. Okay, thanks. And with respect to like, say the number of atoms, like the maximum number of atoms per configuration and like the coverage, can you, say a few words on that?
What do you mean with, so just maybe to be clear. So this is the normal, also normal is a big word, but like we're basically training one model per system, which means we have, let's say for paracetamol,
okay.
Each model has, in this case, let me go back.
Just
like paracetamol, 10,000 different configurations, sampled randomly from 3 independent NVE trajectories in this case. And then we just like try to predict that, basically, yes.
Okay,
But also you could train everything at once. There's nothing stopping you from this. It's just we wanted to check, because we are part of the papers, we're trying to understand what learning works where and how the different systems impact the performance. This is why we train one model per system. That's what I meant with when you look at the early equivariant machine learning potential papers, they had basically one model per system just to understand also and to show the performance what you get. Obviously, you could get better performance if you train on quartz at different temperatures and maybe different phases. Then you could probably extrapolate and interpolate way better. But this is not what we did here, just also because we wanted to really understand how does the time step impact the performance in the long term. But this is definitely an interesting question you're asking.
Okay, yeah, I guess I'm a bit too used to now like these foundation models that just train on everything.
I mean, we're not here, we're not there yet.
Yeah, but it makes sense to start like these so you can actually control the different variables.
Yes.
Okay.
Yeah, I mean, definitely important to kind of make clear this kind of discrepancy, right? Because long-term wise, yes, there's nothing apart from maybe data right now, because there's very little high accuracy NVE trajectory data from training the foundation model on this, and then you could validate that as well, and that would maybe enable you to optimize the model performance better to understand where are shortcomings and so on. But yeah, that was just to kind of get the community basically thinking there's other ways apart from MLIPS how we can accelerate molecular simulations, and basically it can work, but we need to scale it. That's I think is the TLDR. Yeah.
Okay. And did you compare against any of these machine learning force fields, or was it like it takes too long? You don't think it's gonna work anyway?
The point is, we didn't compare in terms of like accuracy. We compared in terms of like we knew this kind of like benchmark of like 1 nanosecond a day, and we basically were trying to kind of like how much can we stress this with not kind of going crazy. There's work where people trained on a big amount of trajectories, and we were basically want to make sure that you can train this on, in theory, ab initio data. We didn't train ab initio data, I want to make this clear, but we didn't want to kind of incorporate like 10,000 trajectories or something. We didn't compare to machine learning force fields because we would have need to train the model or these models on the kind of same level of theory, and it felt first of all weird to train on a machine learning model on a classical force field. So we didn't really go into details there. But when I compare the VDOS, for example, and maybe it's not like that common anymore, but back in early 2020, we looked at the VDOS and we computed these kind of overlap scores and checked how good are these, and then there we know that like 90% and above is really good, and that's what we get. So this is what we compared. The energy distribution would have been difficult to compare with an MLIP. I agree that maybe things like the free energy profile or maybe the diffusion coefficient and the RDF to compare would have been nice. However, I think the RDF is very hard to kind of see a distinction compared to MLIPS probably, because I think this is really spot on. The diffusion coefficient, maybe, yes, and the free energy profiles, I would say yes. That would be an interesting comparison to make. It's just maybe we felt weird to train a machine learning potential on a classical force field. But yeah, definitely an interesting comparison.
Okay. And I have one last question regarding the architecture.
Yes.
So since you're predicting velocities and delta R, so you're just using the L=1 readouts, unlike machine learning potential that use L=0.
Yep. Correct.
Okay.
Yeah.
And
So that's correct. We like the model uses up to L=2 as well, but the readout is only L=1. And actually, it's really nice that we don't have to do backprop, because I think that makes it faster as well. To get the forces, as in like in the potential.
And do you think adding a loss and a constraint on the L=0 could maybe help? Like, as in, say, you predict energy or something like that. Would it help at all?
I think that so I think it's an interesting question, and I think we were looking into this like a year ago. We were starting thinking like, well, because I mean we are in NVE, so we actually know what the new energy is. We know it's constant, right? So there's definitely something to think about. I think we didn't invest enough time looking back at it now, because MLIPs are just, I mean, we had this discussion at the beginning of the talk, right? That MLIPs are just like, if you want to have an energy prediction, you need to make a lot of, like, smoothness is a big kind of thing. You need to make sure that this is like obeyed. And there's a lot of other things you have to incorporate in. And I think back then we didn't have probably the patience to kind of incorporate it back then. But definitely it's an important and interesting question to consider for the future if you want to add energy to that. Yes.
Okay. Thanks for that. Yeah, I think that's all my questions. Anyone have any questions? Or it seems that it's pretty clear.
I mean, it's always good if it's clear, no? I mean, I'm
yes.
down to ask critical questions. I mean, this is not a problem.
Yeah. Okay, then great. I guess we can finish.
No,
Thank you so much, everyone, and thank you so much for presenting. It's pretty nice work. We'll upload the video to YouTube, so if you want to rewatch it, it'll be there. And yeah, again, thank you so much.
No, thank you, Lewis, and thanks everyone for listening. Thank you.
All right, have a good day. Bye.
Bye, YouTube. Bye.